Okay, so we were just introduced to power series. We learned what a power series is, and now we're going to work some example problems where we're going to be given a power series and we want to determine its radius and interval of conversion. Now you might be saying, well, we'll determine its radius and interval of conversion if there is one, right? Maybe there isn't. Maybe it doesn't converge anywhere. Well, no, remember when it comes to power series, at the very least, it's going to be convergent at its center point. Every power series is convergent at its center point. So the x, we've got a power series. Any power series is like you've got some c sub n, right? It's a formula with an n in it. You plug in the n, you get a constant, times just a power term. So at x is equal to a, every single power series is convergent. And furthermore, if it converges at more than just its center point, then it's always going to be some equally spaced interval around the center point. So you're going to have, it'll be either only convergent at its center point and that's it, or you'll have a radius of convergent to where it's convergent at plus or minus the same distance from A. And so the radius of convergence is like the radial distance, like not the total length of the interval, but just the length of one half of the interval, right? The distance from the center point. So you'll have the radius of convergence, and then you just write out what the actual interval is, or it could be convergent for all x, and so the interval is plus or minus infinity. That's the only three cases you can have. You cannot have like an interval that's not centered at the center point. Like that's not going to be a convergence interval for a power series. Okay, so when it comes to power series, which that's the only type of series we're dealing with for the rest of this chapter, it's all about power series, right? That's what a Taylor series is. That's what how we're gonna represent functions as series using power series. It's all this form right here. A c sub n, which is some function of n where you plug in the n and you get a constant. It depends on the n, multiplied by this power term here. This power term here, x minus a to the n. So, but a lot of times you'll see a power series centered at 0, so you'll just see it. There'd be an x to the n is all you'll see, with a bunch of n terms all around it, and that's just a power series centered at 0. A is equal to 0. Okay. Now, so how do we determine the radius and interval of convergence, right? Which it means for what values of x is this series convergent? Well, we just test it using any of the methods we've learned to test a series for convergence. Now, but when it comes to power series, we're dealing with this exact same form every time, this c sub n times x to the n. A lot of these powers determining the convergence of a power series problems are set up very well for the ratio test or the root test, or sometimes the root test, but most of the time the ratio test. Right, because it's this exact same form every time. This x to the n with a c sub n. It's not every single time, but a lot of times, if you're finding the interval and radius of convergence of a power series, you're gonna use the ratio test to figure that out. But it's not every time. Maybe you might have to, depending on the c sub n, maybe you'll have to resort to another one of the methods that we learned. Okay, but let's go ahead and do the ratio test. So the absolute value of a sub n plus 1 over a sub n, okay, and this is a sub n, right? You can imagine that. So when we're finding the radius of the interval of convergence, you're thinking about how within that interval you can pick a value of x. So once you pick a value of x, what happens? Well, now you just have this function of n. Once you pick a value of x, now you've got a series just like we dealt with in the convergence testing sections. That's the idea, okay? So I'm saying all of this is the a sub n. Like this is the c sub n, the n portion of the power series, but all of this is the a sub n in regards to this ratio test formula. So now, but another thing to note, though, when we did like the ratio test in the convergence testing sections, we a lot of times we could just get rid of the absolute value because, well, here we had the -1 to the n, or we could just remove the -1 to the n and get rid of the absolute value because like the function of n was always positive, the n expression. Well, here we have to be a little more careful because we've got this x here, and x is not going by this n to 1 to infinity. X can be any number you want. I mean, unless it specifies otherwise, but in the majority of the time for these power series, x can be whatever. So we have to be a little more careful with when it comes to the absolute value. So we're going to go ahead and leave it on. Now we can go ahead and get rid of this -1 to the n. But, okay, we've got the absolute value of, so n plus 1 times x to the n plus 1 is going to be x to the n times x over 1 times, and then we'll have, so n x to the n. All right, so these cancel, and we've got n plus 1 over n times x. Okay, so we can take out this n plus 1 to the n, right? We could do this because that's always positive. And we haven't changed the expression. N plus 1 over n going from 1 to infinity is always positive. But we can't remove the absolute value for the x because x could be negative. Okay. So what do we do next? How does the ratio test work? What is this? This is the absolute value of a sub n plus 1 over n. We've simplified it to this. So what do we do now? Well, with the ratio test, what we do is we take the limit as n goes to infinity of this a sub n plus 1 over n. Well, x is not a function of n, so we can take this out of the limit. Okay? Now, what does this limit equal to? Well, that goes to 1. So this limit, the limit as n, well, okay, so we've got the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n is equal to the absolute value of x. Okay, but how does the ratio test work, though? For this to be convergent, what does this limit need to, what does this limit need to be? This needs to be less than 1. It needs to be convergent and less than 1. So it couldn't be negative infinity. It needs to be convergent, and that value that it converges to needs to be less than 1. So there we go. We've got this absolute value inequality here. All right. Well, how do we solve an absolute value inequality? Well, we worked these exact type of problems in algebra. So going back to we did this in the algebra playlist. Go check it out. But from the algebra textbook, here's, some simple absolute value inequalities. This is a simple one. If you got the absolute value of an expression is less than a number, like a constant number, that's equivalent to this. The expression is less than k and also at the same time greater than minus k. So we can solve this by saying that x is less than 1 and greater than minus 1. Okay, and so the radius of convergence is going to be 1. We can see it's centered about the center point. We can see the center point is 0. X minus a to the n, a is 0. It's centered, and that's going to be the case every time. And you go 1 in either direction. So the radius of convergence is 1. Now, the interval of convergence, we're not done yet because we need to, maybe we have this, or maybe we have this, or maybe we have this, or maybe we just got this. So we need to test why do we not know what happens at the endpoints? Because this test is inconclusive at the endpoints, the ratio test. It's inconclusive when it comes to the endpoints. If we try to do the ratio test, we would get this limit is equal to 1, which is inconclusive for either endpoint. So we need to use any of the methods that we we learned in the convergence testing sections to find out if this is convergent at the endpoint. So, okay. Let's check x is equal to 1. So we've got right, because 1 to the n is always 1. Okay. Well, do the divergence test. What is the limit as n goes to infinity of this is the a sub n? This is divergent. It goes to, this n goes to infinity, but then with the minus 1, it's oscillating, so this is divergent. So it diverges when x is equal to 1. What about when x is equal to minus 1? So we've got minus 1 to the n times minus 1 to the n. So this is 1 to the n, which is 1, so just n, but this is divergent as well. So the interval of convergence is this. Well, we could write it, I think they want us to write it like this. This is the interval of convergence. Yeah. Okay, ratio test. And you see, this is a power series, right? What is the, again, I just want to hammer this home. Any power series is, well, x minus a in general, is in this form. What's the c sub n here? It's 2n minus, it's 1 over 2n minus 1. The a is 0, right? Don't forget that. It's these power series is the same exact form every time. Okay, so ratio test. And then, so that the c sub n was 1 over 2n minus 1, but all of this is the a sub n, right? The idea is you can pick a value of x, right? This is a function of x. You plug in, it's a function of x, and we're trying to find what the domain of this is, right? Let's come back here. That's another big point. So this is a function of x with domain minus 1 to 1, not including the endpoints. You can plug in, it's convergent. You plug in any value between minus 1 and 1, and you're going to get a value, right? That's the whole point of an infinite series, is convergent to a number. You plug in any value between minus 1 and 1 into this function, and you get a actual value out. It's a function. You could graph this. And the way it works is, because it's weird to look at it this way, but it's because once you pick a value of x and then you get rid of the x, right? And you're left with just an expression with just n's in it. And we know how to analyze that. That's what we spent the first 5 sections analyzing, a series with just an a sub n to see when it's convergent. So that's the idea. Once you pick an x, then this becomes just like any of the series we've analyzed in the convergence testing. All right, so we're not going to get rid of the absolute value. Okay, 2 times n plus 1 minus 1 is what? 2n plus 2 minus 1, 2n plus 1. Okay. So 2n plus 1, and then x to the n plus 1, we'll go ahead and separate it like this. Then you've got x to the n. Okay, so 2n minus 1 over 2n plus 1. As n goes to infinity, that's always positive. So we can just take that out of the absolute value, and we're left with this. So now what is the limit as n goes to infinity of this? Well, okay. We could just take the absolute value of x out of the limit. And what is this limit? That's going to be 1. So once again, we've got, and so the radius of convergence is 1. In the interval of convergence, we don't know. Oh, this is centered about 0. So, okay. Well, we know it's going to be, but we just need to check the endpoints. We know the interval convergence is going to be 1 to minus, or minus 1 to 1, but we need to check the endpoints. All right. And again, for the endpoints, you're not going to be able to use the ratio test. Okay, when x is equal to 1, we've got what? Now, this is like the harmonic series. We can use a comparison test here. So this should be divergent. So 1 over n, how does that compare to 1 over 2n minus 1? Well, this is, well, 1 over 2n. Let's do that. This is always greater, right? Because this is smaller. Well, this is, right? This is divergent, but this is always smaller, so this is divergent. So x is equal to 1, it's divergent. What about x is equal to minus 1? Well, this is, I believe it's going to be conditionally, this is going to be convergent, because it's like the alternating harmonic series we know is convergent. So, okay, how do we do this? The alternating series test. Alternating series test, we've got a b sub n is 2n. There's the b sub n, right? This is the positive portion of the alternating series. Is this decreasing? Is b sub n plus 1 always less than b sub n, at least at some n going to infinity? Yes. So now we just take the limit as n goes to infinity of this, and we can see that's equal to 0. So by the alternating series test, this is convergent. And we expected that because it's like similar to a harmonic series with the alternating portion. So, okay. Therefore, it's convergent between when x is less than 1 and greater than or equal to minus 1. So there's the interval of convergence and the radius of convergence. Okay, so, okay, I really want to hammer this home, that this exact same form every time. Here's the c sub n and x minus a to the n. The c sub n we can see is 1 over n factorial, and a is equal to 0. Right? Power series. That's a power series. If it doesn't have a form like this, then it's not a power series. Just because you see a series that has an x in it doesn't mean it's a power series. The power series is not a series with a variable in it. Not at all. It has to be a form with like what I just wrote out. All right, so ratio test. Okay, we can't just get rid of the absolute value like we did for the convergence testing. Okay, so x to the n plus 1. Okay, n plus 1 factorial we're going to want to write like this. Okay, and then, all right. Oh, wait, we had the absolute value. Okay. The 1 over n plus 1 is always positive, so we could take that out. Okay. Okay, so we got the limit as n goes to infinity. Now this is this is a little bit different. Let's take out the x term. Okay, this time this goes to 0, not 1. Okay, so we've got the absolute value of x times 0, or something infinitesimally small. This is always going to be 0, which is less than 1. So here, no matter what x we plug in, you could plug in x is equal to 10 billion. I mean, as long as it's not infinity. Infinity times 0 is indeterminate, but x is not infinity. You're going to get 0. There's something very close to 0, which is less than 1. So the interval of convergence here is minus infinity to infinity, and the radius of convergence is infinity. Okay, what is the you don't have to do this, but okay, this is a power series. Every single power series has a form like this. If it doesn't, it's not a power series. Just because you see an X in a series doesn't mean it's a power series. Here, the A is equal to 0, and the C sub n is equal to, right? So it's a power series. Let's do the ratio test. So, okay. X to the n plus 1 is x to the n times x. Then we've got n plus 1 to the 4th, and then 4 to the n plus 1 is 4 to the n times 4. Then we've got okay, that cancels. So we've got okay, so we can take out the, this is always positive. Okay, so we've got the limit as n goes to infinity, and then we can take out of this the limit 1/4 absolute value of x, and then okay, and we know this limit here, we've got the order, the numerator is 4, order the denominator is 4, and the coefficients are both 1 on the 4 term. This is going to be 1. So, all right, so we've got the absolute value of x is less than 4, and we saw how to solve this. Okay, so this is going to be centered about 0, so the radius of convergence is 4. And we're going to have minus 4 and 4. We just need to check the endpoints. Okay, when x is equal to 4, we've got, so 4 to the n this is a P series, and it's convergent. So at x is equal to 4, that's in the domain. Okay. What about x is equal to minus 4? So minus 4 to the n, that's going to be minus 1 to the n. So, okay, well, this is, what is the series of the absolute value of this a sub n is what we just looked at, the P series with P is equal to 4. That's convergent. So this is absolutely convergent, which means that this is convergent. So there's the interval, right? That's the domain. This is a function of x. And you can plug in any value between minus 4 and 4, including minus 4 or 4, and you're going to get something out. Okay, there's your C sub n. There's the x to the n. A is equal to 0. So let's do, okay, we can ignore this minus 1 to the n, but we have to keep the absolute value because this x to the n, we don't know if it's positive or negative. Okay, so we've got 4 to the n plus 1 is 4 to the n times 4. X to the n plus 1 is x to the n times x. Okay, now we've got then 4 to the n times x to the n. Okay. So we can take out, I mean, let's write this out. It's kind of confusing. So okay, so we can take out what's always going to be positive. And there we go. This needs to, well, no, we need to take the limit as in approaches infinity of this, and this absolute value of x has nothing to do with n, neither does the 4. So we've got, well, okay, the terms, the order of the numerator and denominator are the same, and the coefficients in front of the highest order terms are the same. So that means that this limit is 1. So this limit is 4 absolute value of x. This needs to be less than 1 to be convergent. But it doesn't tell us what happens when it's equal to 1, which is why we have to test the endpoints. But okay, so we've got the absolute value of x is less than 1/4. Absolute value inequality, again, going back to this. We have the absolute from algebra. We have the absolute value of an expression of x is less than k. That's equivalent, less than a constant. That's equivalent to this and compound inequality here. So x is less than 1/4 or greater than minus 1/4. So the radius of convergence we see is going to be 1/4, centered about 0. And there's the interval, but what about the endpoints? Okay, when x is equal to 1/4, what do we have? So, okay. You've got 4 to the n times 1/4 to the n. That's 1/4 to the n, right? 1/4 to the n, you can bring in, distribute the n with properties of exponents, right? So like a over b to the c is equal to a to the c over b to the c, but 1 to the n is just 1. So, okay. So this is, right, because these cancel. So, okay, now this is, so do the alternating series test. The b sub n is, yeah, this is going to be conditionally convergent, right? Or no, this would be absolutely convergent. We don't even need to do the alternating series test. Just do the absolute value series. This is a p series. Oh, but p is less than 1. So no, okay, we need to do the alternating series test. This should be conditionally convergent. So that series was divergent, but b sub n, okay, so now is this always decreasing? Yes, it is. So now what's the limit? This is equal to 0. So by the alternating series test, this is just convergent, conditionally convergent. So that was at 1/4, so that's convergent. Okay, what about when x is equal to minus 1/4? So here we've got, and then 4 to the n, and then minus 1/4 to the n. So we would get minus 1 to the n, and then, okay, so we've got minus 1 to the n times minus 1 to the n. That gets rid of that alternating portion. And that's a p series where p is less than 1, so this is divergent. So there you go. There's the radius and the interval. Okay, we see here's the c sub n, and here's the x to the n where the a is equal to 0. All right. So we've got 2 to the n times 2. Okay, n plus 1 squared is what? So, okay, n plus 1 squared is n squared plus 2n plus 1, and then plus 1. So n squared plus 2n plus 2. Okay, and then n plus 1, and then x to the n times x. All right. Now you've got 2 to the n squared plus 1, and then n like that. And the absolute value. Okay. So, all right. Let's write this out. This can get confusing here. So is that everything? N plus 1, n squared plus 1, and the x. Then a 2 to n, yeah. So the n term is always positive. So we've got okay. So the limit as n approaches infinity of this can bring out the absolute value of x. And we've got, so I mean you could see it's going to be, you're going to have a 2n cubed in the denominator and then a 1n cubed in the numerator. So this limit's going to go to 1/2. Right? I mean, this isn't a lesson on limits, but so if we expand this out, n cubed plus n squared plus 1. So plus n squared plus n plus 1. Here we've got 2n cubed plus 4n squared plus 4n. Right? We know if we divide the numerator and denominator by n cubed, and as n goes to infinity, you're left with 1/2. Okay, we need this to be less than 1, so the absolute value of x is less than 2. So x, so the radius is going to be 2, centered about x is equal to 0. But what happens at the endpoints? Okay. When x is equal to 2, what do we have? So 2 to the n over 2 to the n, so we're just left with this. Okay, the test for divergence isn't going to work. This limit goes to 0. We can do a comparison test. So the b sub n we'll bring in is n over n squared. So how does 1 over n compare to n squared, n over n squared plus 1? Well, this is n over n squared, so it's just this 1 is the difference. Well, that means that this is always smaller, right? This is a little bit bigger, so this is all smaller. So this is a p-series that's divergent, but this is always greater, so that doesn't tell us anything. What about the integral test? So can we replace n with x? And there's no issue. And it looks like that this is always decreasing. You know, as x squared rises faster than x, but we can just verify for 100 to be mathematically 100% sure. So derivative of the top times the bottom minus derivative of the bottom times the top, all over the bottom squared. Okay, x squared plus 1 minus 2x squared is 1 minus x squared. If we take out a minus here, we get x squared minus 1. Okay, no, that's not going to do anything. So when does 1 minus x squared equal 0? When x is equal to minus 1 or x is equal to 1. So let's plug in x is equal to 2 into this derivative. So this is going to be positive. So, okay, you got 2 squared plus 1 is 5 minus 2 cubed is 8 minus 3. So it's going to be negative. The derivative is negative all the way to infinity once you get past n is equal to 1. All right, so we can do the integral test. So what is the going from 1 to infinity? This is the limit as t approaches infinity. And we did a bunch of problems like this. You know, I'm not going to talk about how to do the integral test. We've already worked a bunch of problems on convergence testing. Okay, so let's come off to the side and evaluate this integral. So if we say that u is equal to x squared plus 1, then 1/2 du is going to be equal to x dx, right? Du dx is 2x. Du is 2x dx, divide both sides by 2. Okay. When x is equal to 1, u is equal to 2. When x is equal to t, u is equal to t squared plus 1. We could take out the 1/2, and then you've got 1 over u du. Okay, so t squared plus 1, so that's always going to be positive because we're going from 1 to infinity. So, but even if it wouldn't matter either way because t squared plus 1, so we've got minus natural log of 2. Okay, and so this is there's the integral, and so if we put that in here, we've got the limit as t approaches infinity of this. This is going to be infinity, divergent. So you can't use 2. Okay, what about when x is minus 2? So what we've got is the exact same thing as we had with x is equal to 2, but it's alternating. Well, it should be alternating. No, I didn't say that right. Exact same thing as we had before, but we have the minus 1 to the n, which usually means it's alternating, but you have to check the expression outside of that minus 1 to the n to make sure that it doesn't have positive or negative terms, and this doesn't. So it is alternating. We've got minus 1 to the n, and then 2 to the n over 2 to the n. So you just have, so that's alternating. Let's do the alternating series test. This is always positive, and we can see this is always decreasing. And we know because we just verified, we just took this derivative, f of x, that's always decreasing. So the alternating series test says we just have to look at this limit of this b sub n. This is equal to 0, which means that this is convergent by the alternating series test. So we have this is conditionally convergent, right? The conditionally convergent because the absolute value of this is not convergent, but it's like the harmonic series, right? The harmonic series, this is divergent, but this is convergent. It's conditionally convergent. So there we go. Centered about 0. Okay, so what do we have here? Is this a power series? Yeah, the C sub n is, and the A is equal to 2, positive 2, right? If you match this up here, positive 2. Because it's positive 2 because when you think about a function, right, we've shifted the function to in the positive direction. That's what when you shift a function like that, if you subtract a constant from the x term or terms, in this case just one term, that means you're shifting it in the positive direction, because when you plug in positive 2, you get 0. That's the 0 point. So we're centered about here, x is equal to 2. It's a power series. And so what that means is that if we do have an actual radius of convergence that's not 0, then it's going to be centered about x is equal to 2. That's the only option. It's not possible for us to get a radius of convergence of 3 and then have like this. That's not possible because this is centered at 0. It needs to be, if we had a radius of convergence of 3, we would know 100% that we're going to have, so 2 plus 3 is 5, 2 minus 3 is minus 1, and then the endpoints would be either included or not included. But we would have this 100% if we knew the radius of convergence was 3 every time. We could not have this is centered about minus 4 with radius equal to 3. No, that's not possible. You're either going to have the only point of convergence is the center point. Every power series converges at its center point, and that's so the radius. In that case, the radius convergence would be 0, and the interval of convergence would be, in this case, would be 2. Or you have like a radius of convergence that's a finite value not equal to 0, and you have like a finite interval of convergence centered about the center point, or the radius of convergence is infinity, and the interval is minus infinity to infinity. All right, so now the ratio test. So, okay, so we've got x minus 2 to the n plus 1, so we'll do x minus 2 times x minus 2 to the n, right? And then n plus 1 squared plus 1 is going to be what? N squared plus 2n plus 2. If you expand that out. That's n plus 1. Well, let me, okay, I don't want to go too fast. So we've got n plus 1 squared plus 1, right? Now we've got n squared plus 1. Okay. So now n plus 1 squared plus 1 is n squared plus 2n plus 2. So n squared plus 2n plus 2. All right. Then you've got n squared plus 1. Okay, so we can, the n terms are always positive, so they don't need to be in the absolute value. Okay, now what is the limit as n goes to infinity of, well, we can take out this, and we've got, this goes to 1, so you've got, okay, now we need this to be less than 1 in order for convergence. So absolute value inequality, an expression is less than a constant is equivalent to, we just put that expression between the constants. So we've got that expression is less than 1 is greater than minus 1. But now we're not done. We need to add 2 to this, to every single part of this. So we've got minus 1 plus 2 is 1. 1 plus 2 is 3. And there we go. This is centered about, if we use 2 as the center point, we go plus 1 or minus 1. So the radius is 1. You see, we're centered at 2 here. On both sides of 2, you've got plus 1, and on both sides of 2, you've got 1, a unit of 1. 2 plus 1 is 3, 2 minus 1 is 1. All right, so we've got 1, 3, just need to look at the endpoints. Okay, when x is equal to 1, what do we have? So you've got minus 1 to the n. Well, this is going to be convergent. This is going to be absolutely convergent. I mean, let's go through the proof, but you can see because it's like, it's a p series. You can't, it's not exactly a p series because you've got the n squared plus 1. So like, okay, we do the absolute value series. If 1 over n squared is convergent, then I would bet that 1 over n squared plus 1 would be convergent. It's so similar to that convergent p series, but okay. Let's bring in this for comparison. This is bigger, so This is always greater. This is convergent. So the series with the terms that are always less than that series are going to be convergent as well. So this is absolutely convergent. That means it's convergent. So, okay, now let's do x is equal to 3. So we've got 1, just 1 over n squared plus 1. We just saw this was convergent. So there you go.